Welcome students for today's lecture on design of circular water tanks with fixed base. Now in the previous design, we have designed a circular water tank with a flexible base. So what was the difference between these two was, in the circular water tank with a flexible base, the base was flexible. And how it was made flexible? By using the tar component or bituminous component. Now in this design, we have water tank with the fixed base. So we are going to design a circular water tank with fixed base. So let you show. So this is the base portion, and what will happen is, in this component the base slab is directly a concrete structure and is a monolithic structure. But in the circular water tank with the flexible base, what had happened is, whatever the base slab was there even the bitumen component was there. Okay, now let us solve an example for designing a water tank with a fixed base. So we are going to design a circular water tank today, and in this design we will make the use of IS code IS 3370 part 4 for the design. That means using the application of IS 3370 part 4, which gives the guidelines for the liquid storage structures. So let us see. So the question taken up is, design a circular water tank with fixed base for a capacity of 4 lakh liters. The depth of the water is to be 4 meters. Freeboard 200 mm. Use M20 grade concrete and grade I mild steel. So this is how is the question. So also they have given the permissible direct tensile stress in concrete 1.2 Newton per mm square. Permissible stress in steel in direct tension 100 Newton per mm square. It is given. Sketch the details of reinforcement in the tank walls. Now, in any of the question, if this permissible direct tensile stress in concrete and permissible stress in steel in direct tension is not given, then we can definitely refer IS 3370 part 2, which is the guidelines for RCC structure. So if note that if in question these two components, that is direct tensile stress in concrete and permissible stress in steel is in direct tension is not given, you have to take it from the design tables which are given in IS 3370 part 2 for RCC. Depending upon the grade and mild steel, you will get these components. So this is given. Now let us see. Now data. Capacity of the tank. So in the question you can see here it is given, design a circular water tank with fixed base for a capacity of 4 lakh liters. That means the capacity of water tank is 4 lakh liters. So after converting we get 400 meter cube. Okay, then the depth of the water is to be 4 meters. So depth of the water is 4 meters. Freeboard given is 200 mm. So the freeboard is given is 200 mm. The density of water is taken as 9.81 kilonewton per meter cube. Then M20 grade concrete and grade 1 steel. This is the general data of the circular water tank. Now regarding the second step, that is permissible stresses. So you can see the direct tensile stress in concrete sigma CT is given as 1.2 Newton per mm square. You can see here it is given. Permissible direct tensile stress in concrete 1.2 Newton per mm square. So it is a concrete, so we have named it as sigma CT. Similarly, tensile stress in steel sigma ST is 100 Newton per mm square. So this here you can see permissible stress in steel in direct tension 100 Newton per m square. So I will denote it as sigma ST. Now let us see the dimension. So I will draw a rough diagram for the dimensions of the tank. Now just we will see what all I have. So it is a circular water tank. So these are one tank walls. This is small t is nothing but the thickness of tank wall. This is the base slab and this is the thickness of the base slab or depth of the base slab. So the water should be 4 meters. 4 meters. So depth of the water is 4 meters and the free board is 0.2 meter, that is 200 mm. You can see here. It is given as 200 mm. So the total depth of the water tank becomes 4.2 meters. Now let D be the diameter of the water tank. Now 11.5 meter is put here, but it needs to be calculated. Why we are drawing this? Because we need to calculate the diameter. Now let us see how the diameter of the water tank is found out. So as it is circular, so I can make the use of volume and equate it to volume. So let us see, pi by 4 into d square into h. So this is pi by 4 into d square gives the area into the h, that is 4.2 meters here total depth, equal to volume of water 400 meter cube. You can see here. So it is converted to 400 meter cube. So equating the volume of water or capacity to the dimensions of the circular water tank. So pi by 4 into d square into 4.2, where 4.2 is h, and equal to 400 meter cube. So this is the capacity in liters, that is 4 lakh liters. So substituting, we get d square is equal to 121.26. So making a root of it, we'll get a diameter d is equal to 11.01 meter. So we are rounding off it to 11.5 meter. So this is what I have written here. Diameter is equal to 11.5 meters. So we got the dimension now. So the diameter is 11.5 meter. Depth of the water is 4 meter. The free board is 0.2 meter. So the height is 4.2 meter. Now next what we have to design is the thickness of the base slab and thickness of the tank wall and also the hoop tension and other components. So let us see. The thickness of walls and the base slab are assumed. So the thickness of the wall and base slab are assumed as 200 mm, or you can also take it as 30h plus 50, where h, capital H is nothing but the total height of the tank wall. So 30 into, so total height is 4.2 meter, 4.2 plus 50, which is 176. So I have rounded it off to 200 mm. So we have taken it as thickness of tank wall and base slab as 200 mm. So the assumption is this. So this is how it has to be found out. So the tank wall thickness is 200 mm as well as the base slab thickness is 200 mm. Now let us see the application of the code book before getting to the fourth point. So what is fourth point? It is nothing but bending moment, ring tension and ring shear. Okay, so remember we have to find out whenever a rigid base or a fixed base is there for a circular water tank or the uh, uh, so rectangular tank. So we have to find out the bending moment, ring tension and ring shear. So here we will see in the codebook application. So this is the codebook. So we have to make the use of IS 3370 part 4 1967, which is a codebook for the concrete structures for the storage of liquids. So part 4 is for design tables. So as discussed earlier, part 1 is general considerations, part 2 is for RCC, part 3 is for PSC and part 4 is for the design tables for computing the forces onto the water tank. Now what we are going to, what this codebook has is, so here you can see there are a list of tables given. So they have given clearly for rectangular tanks. So ours is a circular tank now. So they have also discussed about that circular tank. So cylindrical tanks can be taken as circular tanks. So obviously this is what it is there. So here we will see 3.1 ring tension and movements in the wall. So remember, you can see here we have put bending moment, ring tension and ring shear. So it is given in the codebook here. So 3.1.1 discuss with wall with fixed base and free top and subjected to triangular load. Now this is the case which we have now here. So you can see if in our diagram, so the tank wall here is the water stored So we have free top, so there is no lid or no cover, so it is free top, and this water will exert a pressure on this tank wall which is of a triangular load, So and the base slab is fixed. So we have to design a circular water tank with fixed base. So walls with fixed base, that means a fixed base slab, and top nothing cover is there, so free top and subjected to triangular load. So the water which is present in the tank here will create a triangular load onto the walls. So this is our condition. Now let us see what is there in this. So for walls with fixed base and free top subjected to triangular load, that means cylindrical wall with fixed base, so top is free and subject to triangular load. So it is given in figure 3. So you can see the figure 3 says that walls with fixed base and free top subjected to triangular load. So this is how the thickness of wall will be there, base of the slab will be there, and this is how the triangular load, that is water pressure, will act on the tank walls, wherein this is omega into h, this is total height h. So let us see what has been given. Walls built continuously with their footings are sometimes designed as though the base was fixed and top free. Although strictly speaking, the base is seldom fixed, but it is helpful to start with this assumption. So assuming, though it is not fully fixed, but we will assume it as a uh, fully fixed, and then go on to the design procedure for more correct condition. So that is ring tension at various heights of the wall of cylindrical tank fixed at the base. Free at the top and subjected to a triangle load are given in table number 9. So remember, so the ring tension to be computed are given in table number 9, and our condition is circular water tank with fixed base, free top and subjected to triangular load. So remember, the ring tension has to be computed according to the table number 9 which is given in this code book. Then the movement in a cylindrical wall for fixed base, free top and triangular load is given in table number 10. So remember, the bending moment in the walls is given in table number 10. Then the coefficient of shear at the base for a cylindrical wall is given in table number 11. So now did you understand why we have taken the fourth point as, just I will show it to you. So we have taken the fourth point as bending moment, ring tension and a ring shear. So it is given here. So ring tension, the bending moment and the coefficient for shear. So the bending moment, the first point here is a bending moment here. So this will be computed according to the table number 10 for this condition, which is circular water tank with fixed base, free top and subjected to triangular load. Then second, ring tension. So the ring tension is calculated according to the table number 9, remember. Then ring shear, that is nothing but the shear at the base. So coefficient for the shear at the base is given in table number 11. So remember, we have to make use of these three tables to compute the bending moment, ring tension and the shear. So even 3.1.2 is for a different case. Walls with hinged base, free top and subjected to triangular load. Now what is the difference between this and the above is, here it is hinged base, that is not a fixed base, that means it is a flexible base. So here also they have given how to calculate. So the ring tension and the movements at different heights of a cylindrical wall are given in table number 12 and 13 respectively, and coefficient for shear is given in table number 11. So this is the figure 4, you can see here. So this is again the diagram for figure 4, wherein the walls are hinged base, free top and subjected to triangular load. So let us see, the values given in 3.1.1 are based on the assumption of the joint, and the footing is prevented from even the smallest rotation kind shown in exaggerated 4. The rotation required to reduce the fixed base moment from some definite value to say 0 is much smaller than rotation that may occur when normal settlement takes place in subgrade. Okay, it may be difficult to predict the behavior of subgrade and its effect upon the restraint at the base, but it is more reasonable to assume that the base is hinged than fixed, and hinged based assumption gives a safer design. So this is how the condition, the design concept is given. And here also we have to find out the movements, bending moments, ring tension and the shear. So how it is calculated? So ring tension and movements at different heights of cylindrical wall are given in the table 12 and 13 respectively, and the coefficient of shear at the base with cylindrical wall are given in table number 11. So this is how it is to be computed. Now, what is our question? So, if we see the question, I will go back to the question. So, it is circular water tank with fixed base. So, it is a cylindrical tank with fixed base and nothing is there on the top. So, free at the top, and whatever water is there inside will create a triangular pressure on the walls. That's why a triangular load will be considered. So, here they have given again the conditions here. Now even 3.1.3 if you see, walls with hinged base and free top subjected to trapezoidal load now. This is not a triangular load now. So even we have a trapezoidal load. And why it happens? It is given in this. So let us see. In the tank used for storage of liquids subjected to vapor pressure, see vapor pressure, and also in cases where the liquid surface may rise considerably above the top of the wall, as may accidentally happen in case of the underground tanks. The pressure on the tank wall is a combination of triangular hydrostatic pressure plus uniformly distributed loading. So remember, so this is the uniformly distributed loading and a triangular. So water pressure is there. So due to this, this becomes a trapezoidal load now, as shown in the figure B. The combined pressure will have a trapezoidal distribution. So you can see a trapezoidal distribution is there. So which only represents the loading condition without considering the effect of the roof, which is discussed in 3.1.4, that is next class. In this case, the coefficient of ring tension may be taken from table number 12 and 14, and the coefficient for shear will be taken from 11, and the coefficient for movement per unit width will be given in table number 13. So this is the diagram for walls with hinged base and free top subjected to trapezoidal load. Now remember, when the trapezoidal load will come, due to the liquid surfaces, and it is a combination of uniformly distributed load and a hydrostatic pressure. Let us see the fourth condition. So 3.14, walls with shear applied at the top. So table number 6. So here you can see the top there is a covering. So even this will act on the shear load. When the top of the cylindrical wall is doubled to the roof slab, it may not be able to move freely, as assumed in 3.1.1 to 3.1.3. So it will not move freely. When the displacement is prevented, the top cannot expand and the ring tension is 0 at the top. Understood? So if T is kg in ring tension at a point 0 h, when the top is free to expand, as in case of 3.15, the value of shear V can be found out from table number 15. So here you can see it cannot move freely here. So due to this, what will happen? There will be a rigidity a bit. Hence the displacement is prevented. So ring tension will be 0 at top. So tension will be given as minus x V R divided by H, and V is given by H T divided by R x, where x is the coefficient obtained from table number 15 depending upon the ratio h square divided by dt. So this is the figure. So you can see the top is covered here. Now next condition 3.1.5, wall with shear applied at the base. Now here the shear applied was at the top, now here shear applied at the base. Let us see. So the data given in table 15 may be approximately applied in case where shear is at the base of the wall, as in figure 7 you can see here, which illustrates a case in which the base of the wall is displaced radially by application of horizontal shear V having an inward direction. You can see V application here into the inward direction. When the base is hinged, the displacement will be 0. If the base is hinged, the displacement will be 0. And the reaction on the walls will be inward in the direction. You can see it. When the base is sliding, there will be a largest possible displacement, but the reaction will be 0. So this is how the condition is given. Now let us see the next case. 3.1.6, walls with movement applied at the top now. So movement will be at the top. You can see here the movement is applied at the top. So this happens when the top wall of the wall and the roof slab are made continuous, as shown in the figure 8. You can see the deflection of the roof will tend to rotate the top joint and introduce a movement at the top of the wall. So movement at the top of the wall. In such cases, table number 16 and table number 17 will be found useful for preparing the applied movements at one end of the wall when other is free. These tables may also be applied with a good degree of accuracy when the free end is hinged or fixed. So 3.1.7, the data for movements in cylindrical walls fixed at the base and free at the top and subjected to rectangular load are covered in table number 18. And the data for movements in cylindrical wall fixed at a base, free at top, subjected to shear applied at the top is covered in table number 19. So let us just go through what all are the conditions. So if different types of combinations. So when we start with the design of circular water tank here, so the clause number is 3, and the first is how to calculate the movement in the walls and ring tension, why to calculate they have explained. The first condition is walls with a fixed base and free top subjected to triangular load. The second case is walls with hinged base, free at top and subjected to triangular load. The third case is walls with hinged base, free at top and a trapezoidal load. So this trapezoidal load is a combination of uniformly distributed load and the triangular load. Then next is walls with shear applied at the top. You can see shear applied due to the covering. Then walls with shear applied at the base. So walls with shear applied at the base. So this is shear applied, and walls with shear applied and the movement applied at the top. So many are the conditions. Now let us see in which condition our question falls. So we will see. So design a circular water tank with fixed base. That means it is cylindrical tank with walls with fixed base. Correct? That is clear. So first condition is clear. Depth of the water is 4 meters. So you can see if a diagram. So it is open top, and this will create whatever is present will create a triangular pressure onto the walls. As the depth increases here the pressure will be maximum, here it will be minimum, because this exerts a pressure towards center of gravity. So which condition it is out of this? So let us see. So the condition for us to solve is cylindrical tank with a fixed base. Okay, so we have circular water tank with fixed base, that means walls with fixed base. So nothing is there on the top, so free top and subjected to triangular load due to the water. So this is the condition which we have to solve, that is 3.1.1. And according to 3.1.1, what all we have to calculate? Ring tension and movement. So only this has arrived here, the fourth point: bending moment, ring tension and shear. And this has to calculate according to the tables and the clause which we have given. So these are the dimensions: diameter 11.5 meter, 4 meter depth of water, and 0.2 meter freeboard, total height 4 meter, and the thickness of wall we have taken is 200 mm, thickness of base slab as 200 mm. So we will see the design and the continuation of this bending movement, ring tension and ring shear in the next class. Thank you.